Hello students, welcome to Sankalp Learning Solutions. I am Aishwarya Ingimat. Today we shall discuss the synopsis on D and F block elements, right? Okay. So basically D and F block elements andaga, first you all know much more about electronic configurations ಬಗ್ಗೆ ಗೊತ್ತಿರಬೇಕು. ಅದಕ್ಕಿಂತ ಮೊದಲಾಗಿ we should know the elements, the periodic properties of the elements, and that all things you are already studied in your PU1 classes, that is periodic classification of elements. Let me brief out before starting D and F block elements. Let me brief out some of the important characteristics of a periodic table. ಅಂದಾಗ ನಮಗೆ D and F block ಬಗ್ಗೆ ತುಂಬಾ ಚೆನ್ನಾಗಿ ಅರ್ಥ ಆಗುತ್ತೆ ಅಂತ ನಾನು ಅನ್ಕೋತೀನಿ. So see, entire periodic table which is having 119 elements, this entire periodic table is being classified into different varieties of based on different varieties of properties. Yenappa properties depending upon the physical properties, entire periodic table is classified as metals, non-metals and metalloids, right? And you all know which are the metals, what are the physical properties of metals and non-metals, metalloids antandre enu, other properties enu, and where they are situated in the periodic table also. Then apart from that, this periodic table is being divided also into the horizontal rows and the vertical columns. ಏನಪ್ಪ ಅದು horizontal rows ಮತ್ತು vertical columns ಅಂತಂದ್ರೆ, horizontal rows there are seven horizontal rows and 14 vertical columns, correct? There are 7 horizontal rows and 14 vertical columns. So 7 horizontal rows we call them as periods. We call them as periods, and 18 vertical columns we call them as groups. So there are, in the modern periodic table, there are 7 horizontal rows which you call them as periods and 18 vertical columns which you call them as groups. And there is speciality about these periods and groups also. If you look at the period, each period starts with alkali metal. Each period starts with alkali metal and ends with noble gases. It will end with a noble gas. This is about period, noble gas. Then if you look at the groups, 18 vertical columns idava, there are 18 groups and each group is having typical names. So what are the names? For example, group 1 is called alkali metals antivi now. Group 2 elements, they are called alkaline earth metals. Coming to group 13 elements, they are not having any typical name, but we call them with the name of first element, boron family anta antivi. We call them as boron family. Group 14, we call them as carbon family because first element is carbon. Group 15, we call them as nitrogen family, or they are also called as pnictogens. Some property of nitrogen, we call them as pnictogens. Group 16, we call them as halogens. Fluorine family annala, we call them as halogens. Group 16, let me make it a correction. Group 16 is called oxygen family. Yes, group 16 is oxygen family. We call them as chalcogens. And group 17, fluorine family. Rather than calling fluorine, typically we call them as halogens. And group 18 is having lot many names, like they are called noble gases, they are called inert gases, they are called rare gases. So many names are the rare gases. Okay, fine. So these are the groups. I did not speak about group 3 to group 12. These are the groups which we are going to discuss today. The synopsis of these groups are going to be discussed. Okay, so this is another way of classifying the entire elements in the periodic table. There is one more way of classifying the elements in the periodic table. One more way is nothing but the periodic table, all the elements are divided into blocks. They are divided into blocks. As we all know, in the periodic table, the elements are classified on the basis of their electronic configuration. The elements are classified, very important property, atomic property and both, because based on this entire properties of the elements are being discussed, right? So based on the electronic configuration, the elements are divided into blocks. How many blocks? There are 4 blocks. There are 4 blocks of elements and you know it. You have studied about the 4 blocks. Which are the 4 blocks? It is S block, then you have P block, then you have D block, and then you have F block. So these are the 4 blocks of elements. So how is this elements are classified into different blocks? Yav elements S block al barutte pa, yav elements P block al barutte, yav elements D block al barutte, and yav elements F block al barutte. We have certain explanation for that. Yenappa, depending on the type of atomic orbital which the last electron enters, last electron andre we also that in essence we also call it as differentiating electron. We call it as differentiating electron. Differentiating electron andre enu last electron. Depending upon the type of atomic orbital the last electron or the differentiating electron enters, the elements fall into these 4 blocks. That means if the last electron is entering into s orbital, it falls under s block. For example, you take lithium, atomic number is 3. So you write the configuration 1s2, 2s1. You can see here the differentiating electron is entering into s orbital. The differentiating electron is entering into s orbital. Similarly, you take another example, like you take the example of, let me say carbon. Carbon atomic number is 6. So you write the configuration 1s2, 2s2 and 2p2. So you can see here the differentiating electron is entering into p orbital. The differentiating electron is entering into p orbital. Therefore, this particular element falls under which group block? It falls under p block. And you have studied this. You have studied it in your PU1 classes and even in PU2 S and p block elements. So S and p block elements, they are typically called, they are called as main group elements, or they are also called as main group elements, or they are also called as representative elements, because most of the compounds, most of the ores, most of the minerals, they are formed from these particular, and there are properties also on S and P block. So they are collectively called as main group elements or representative elements. So this is a basic introduction about the periodic table and the elements. So now with this particular introduction, let us move to the further part which is required for us, that is D block elements. So with this particular explanation, how do you define D block elements? We define D block elements as the differentiating electron enters into, the last electron enters into D orbital. If the last electron, so what are D block elements? D block elements are the elements in which the last electron enters D subshell. It enters D subshell or D orbital. It enters D subshell. But here we say D subshell of penultimate shell. Very important. D subshell of penultimate shell. So D subshell of penultimate shell. See, in the previous slide we have seen example of lithium. The last electron, the differentiating electron, you can see here, it is entering where? It is entering into second shell. That is, this is the last shell. So it is entering into nth shell in S block elements. This is an example for P block elements. Here the last electron is entering into second shell. This is also last shell. Yes or no? So this is also nth shell. So here we say S and P block elements in a define ಮಾಡ್ತಿರಬೇಕಾದ್ರೆ ನಾವೇನಂತ define ಮಾಡ್ತೀವಿ? We define S and P block elements as the last electron, the differentiating electron enters into S subshell for S block or P subshell for P block of ultimate shell ಅಂತ ಅಂತೀವಿ ನಾವು. Ultimate shell andri, athwa you say nth shell. You say it as ultimate shell or nth shell. But here when we talk about D block elements, it enters the D subshell of the penultimate shell. We'll discuss about it a bit later. Electronic configuration ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ I'll let you know what does this penultimate shell means. Or let me take one example here itself. One of the example of D block element is scandium, whose atomic number is 21. We write it as ನೀವು ಬರೀರಿ configuration 1s2, 2s2, 2p6. You all know how to write the configuration. 3s2, 3p6, 21 electrons ಹೋಗ್ಬೇಕು. Then 4s2, 3d1. You know at electronic configuration ಹೇಗೆ ಬರಿಬೇಕು ಅನ್ನೋದನ್ನು ನಿಮಗೆ ಗೊತ್ತಿದೆ ಅಂತ ಅನ್ಕೋತೀನಿ ನಾನು. We follow 3 principles. ಒಂದು ಆಫ್ ಬಾವ್ ಪ್ರಿನ್ಸಿಪಲ್ ಆಗಿರ್ಬೋದು, ಇನ್ನೊಂದು ಪಾಲಿಸ್ ಎಕ್ಸ್ಕ್ಲೂಷನ್ ಪ್ರಿನ್ಸಿಪಲ್ ಆಗಿರ್ಬೋದು, ಆಮೇಲೆ ಹೋನ್ಸ್ ರೂಲ್ ಆಫ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಮಲ್ಟಿಪ್ಲಿಸಿಟಿ ಆಗಿರ್ಬೋದು. ಸಿ ಆಫ್ ಬಾವ್ ಪ್ರಿನ್ಸಿಪಲ್ ಏನ್ ಹೇಳುತ್ತೆ? ಫಿಲ್ಲಿಂಗ್ ಆಫ್ ದ ಅಟಾಮಿಕ್ ಆರ್ಬಿಟಲ್ ಶುಡ್ ಸ್ಟಾರ್ಟ್ ಫ್ರಮ್ ಲೋವರ್ ಎನರ್ಜಿ ಟು ಹೈಯರ್ ಎನರ್ಜಿ. ಸೊ ಅದರ ಪ್ರಕಾರ 4s ಆರ್ಬಿಟಲ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ಲೋವರ್ ಎನರ್ಜಿ ಅಂಡ್ 3d is having higher energy. I need not give much explanation here ಅಂತ ಅನ್ಕೊಳ್ತೀನಿ, because you know why 4s is having lower energy. You might be knowing n plus l rule. ಯಾವ್ದ್ರದ್ದು ಆರ್ಬಿಟಲ್ n plus l ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ ಇರುತ್ತೆ, that will be having lower energy. So 4s ಅಂತ ತಗೊಂಡಾಗ n is 4 plus l ಏನು s ಗೆ it is 0. So 4 plus 0 is 4, correct? If you see 3d, n is 3, d 0, 1, 2, it is 2d. Therefore it is 5. So 4s is having lower energy than 3d. Therefore filling of the atomic orbitals ಮಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ 4s orbital na naven martivi modlu fill martivi, and you can see here 3d orbital is filled later. So please observe carefully. When you observe carefully here, the last electron is not entering into the nth shell. This is nth shell. Fourth shell is the nth shell, right? So the last electron is not entering the nth shell. Instead, it is entering which cell? It is entering the n minus 1th shell. And this n minus 1th shell is called what? It is called penultimate shell. So this is how we define d block elements. So d block elements andre enu? The elements in which the last electron enters d subshell of the penultimate shell, that is n minus 1th shell. So where are these d block elements? These d block elements, they are located. So d block elements, they are located in 4th, 5th, 6th, and 7th periods. So 4 periods alli barutte d block elements. Yav periods? So they are present in 4th, 5th, 6th, and 7th. 4th period, basically they are having names also. 4th period elements are called 3D series. 4th period elements are called 3D series. 5th period elements are called 4D series. 6th period elements are called 5D series. And 7th period elements are called 6D series. So totally d block alli 4 series barutte. Yavyavu? 3D series, 4D series, 5D series, 6D series. So we will be studying one by one. Basically, now d block elements second PU kalibekadre we concentrate more on 3D series. 5D 6D matartirbekadre we talk about F block elements there. So 3D series ಬಗ್ಗೆ ಜಾಸ್ತಿ ಮಾತಾಡ್ತೀವಿ, and in general the properties of all the elements are also discussed. We'll be discussing synopsis ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ. Okay. So now ಇದು periods ಆಯ್ತು. ಯಾವ್ಯಾವ ಗ್ರೂಪ್ಸ್ ಅಲ್ಲಿ ಬರುತ್ತಪ್ಪ? They fall under from group 3 to group 12. Group 3 to group 12. ಎಷ್ಟು groups ಆಯ್ತಪ್ಪ? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So totally for D block, how many groups are there? There are 10 groups. ಯಾವ್ಯಾವು? Group 3 to group 12. So group 3 to group 12 ಒಳಗೆ ಬರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಎಲಿಮೆಂಟ್ಸ್ ಗೆ ನಾವೇನಂತೀವಿ? D block elements ಅಂತೀವಿ. But when we talk except group 12 elements, these D block elements are called, except, please make a point, except group 12 elements, D block elements are called transition elements. D block elements are called transition elements. Now what is this transition elements appa? Yenidu transition elements antandre? See, nimage ಒಂದು rough figure ತೋರಿಸ್ತೀನಿ. ನಾವು periodic table ಹಾಕಿದಾಗ it is something like this. I'm not taking it exactly, but you all can make out periodic table. Hapa hige ide anta, correct? So this is periodic table, correct? Haudalva? And here there are two groups. Avi eradu groups yavu? Those two groups are lanthanides and actinides. These are F block elements. We'll study it separately. So this is group 1, group 2. Here you have group 3 to group 12. Here is 13, 14, 15, 16, 17, and 18. This is our periodic table. Haudalva? So you have studied about S block. You have studied about S block. You have studied about P block. And you all know the properties of S and P block also. If you see D block elements, where are these D block elements? They are located in between S and P block. Correct? They are located in between S and P block elements. So what is this transition actually? The transition elements are those which possess incompletely filled. They possess incompletely filled D subshell. So D subshell incompletely filled ಆಗಿರುತ್ತೆ, either in their atomic state, ಅಂದ್ರೆ neutral atomic state ಒಳಗಿರಬಹುದು incompletely filled D subshell, or in their most common oxidation state. So they are called these transition elements. ಯಾಕೆ ಅವಕ್ಕೆ transition elements ಅಂತೀವಿ? So transition elements ಅಂತ ಕರೆಯೋ reason, transition elements ಅನ್ಬೋದು, transition metals ಅನ್ಬೋದು. So they have incompletely filled D subshell either in the atomic state or most common oxidation state. So why the name transition now? The name transition is, if you look in the periodic table, across the period, when you move from left to right in the periodic table, you know that electropositive nature goes on decreasing. Howda? excuse me, left to right nodidaga electropositive nature goes on decreasing. So when you move from left to on the left side, there are elements with high electropositive nature. So illi electropositive nature is high, and as you move from left to right, electropositivity is decreasing. So elements with low electropositive nature. So transition elements are nodidaga, since in the beginning the elements are with high electropositive nature, they are going to form the compounds which are ionic. We know this. So high electropositive nature idre compounds are ionic. But when you move from left to right in each series, pratyondu series, illi nimak 3D series baratte, 4D series, here you have 5D series, here you have 6D series. So in each series, if you go on seeing 3D series olage, 4D series, in the beginning, the compounds are ionic, but from left to right, when you move across the series, the ionic nature goes on decreasing and the covalent nature goes on increasing, covalent nature of the compounds. So along the D series, electropositive nature of the element goes on decreasing with the increasing atomic number. Illi 21 ide, here 22, here 23, 24, up to 30 elements are there. So hege atomic number ಹೆಚ್ಚಿಗೆ ಆಗುತ್ತೆ ಹೋಗುತ್ತೆ, ಹಾಗೆ ಏನಾಗುತ್ತೆ, what is happening there? There the electropositive nature is decreasing. So at the elements in the beginning of each series, they will give the compounds which are ionic in nature, highly ionic in nature. But as we proceed further, the elements at the end of the series, the compounds are more with what character? They are more with covalent character. Therefore, there is transition between the properties. So you can see the difference in the properties from ionic to covalent change agad nodta idivi. Therefore, the name is called transition elements. Hence the name, that is transition elements. Fine. So in these elements, as we said, the d electron, the d subshell is being filled. So d subshell, penultimate shell is being filled. That is n-1th shell is being filled. So there are, as I said, there are 4 series. Yavavapa 4 series. Oh, there are 4 series. They are 3D series, 4D series, 5D series, and 6D series. So all the transition elements are metals. All the transition elements are metals. So transition elements anbodu, transition metals no anbodu. So they possess the characteristics of metals. What are the characteristics of metals? We'll be discussing that also. Typically atomic characteristics discuss martivi, but metals antakshana high tensile strength, malleability is there, ductility is there, then thermal and electrical conductivity is also there. Transition elements, they are having high melting and boiling points due to strong metallic interatomic bonding antiv now. So here, yenappa strong metallic interatomic bondings antandre. So here, let us see once again the properties of transition metals. So properties yenappa transition metals idu. In order to understand the properties of transition metals, we need to first understand the electronic configuration of transition elements. So what is the electronic configurations of transition elements? You already know that. The general electronic configuration andaga, when we talk about general electronic configuration of all the D block elements, the general electronic configuration ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ, we write it like this. Noble gas configuration 1s2 2s2 ಬರ್ಕೊಂತ ಕುಂದ್ರೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ. Noble gas configuration n-1d filling of the orbitals penultimate shell ಇದಾಗತ್ತೆ. It will be up to 1 to 10. S block ಅಲ್ಲಿ maximum 2 electrons. So P block ಅಲ್ಲಿ maximum 6 electrons, D block ಅಲ್ಲಿ maximum 10 electrons, F block ಅಲ್ಲಿ maximum 14 electrons. It is known to you all. And ns 1 to 2. Yes, this is the general electronic configuration of all the D block elements. But typically, when I talk about the first transition series, its name is 3D series. So it corresponds to filling of 3D subshell. Yakada 3D series antivi, because it goes on corresponds to filling up of 3D subshell. Then it is having how many elements? 10 elements. It is having 10 elements. Which are the elements? The elements start from scandium with atomic number 21 to zinc with atomic number 30. Okay. This onde series iddu, I will write the electronic configuration. You can see scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. See, students, this is a 3D series. Atomic number 21, 22, 23, 24. Either the configuration because all the properties are being explained by looking at the configurations. So we should know the configuration. Okay, and there are some exceptions also here. So that also we'll be discussing. Fine, fine. Okay, please have a look here. Scandium, my professor had taught me 3D series ಬಗ್ಗೆ ನೆನಪಿಟ್ಕೊಳ್ಬೇಕಾ because maximum frequent questions are from 3D series 4D 5D 6D ಅಷ್ಟು questions ಬರಲ್ಲ so maximum 3D series ಅಲ್ಲಿ ಬರುತ್ತೆ so 3D series ಹೇಗೆ ನೆನಪಿಟ್ಕೊಳ್ಳೋದಪ್ಪ ಸ್ಕ್ಯಾಂಡಿಯಂ ಟಿಟಾನಿಯಂ ವೆನಾಡಿಯಂ ನೆನಪಿಟ್ಕೊಳ್ಳೋಕೆ ಆಗತ್ತಾ ಮೆಮರಿ ಪವರ್ ಒಳ್ಳೇದಿದೆ ನಾನು ಓಕೆ ವೆಲ್ ಅಂಡ್ ಗುಡ್ ಇಫ್ ಯು ಕಾಂಟ್ ರಿಮೆಂಬರ್ ಯು ರಿಮೆಂಬರ್ ಇಟ್ ಲೈಕ್ ದಿಸ್ ಸಿ ಅಲ್ಲ ಪ್ಲೀಸ್ ಗೋ ವಿತ್ ಮೀ ಸ್ಕರ್ ಟಿ ವಕ್ರ ಮನ್ ಫೆ ಕೋ ನಿ ಕು ಝೆನ್. This was my professor. He told me to remember this series and I still do remember this. So what are the series? Elements of this series? Skirti, Vakra, Manfe, Koni, Kuzen. So scandium, titanium, vanadium, chromium, man, manganese, Fe, iron, cobalt, nickel, Kuzen, copper, zinc. Okay. So when we talk about the configuration, so noble gas configuration banbitu argon remains fixed. I'll not write for all the elements, only for one element I'm writing here. 21, 18 aitu, 19, 20, 21. So it is 3D1, 4s2. So penultimate shell is being filled. Titanium, the configuration banbitu 3D2, 4s2. Vanadium, 3D3, 4s2. Chromium, you expect it to be 3D4, 4s2, but it is not 3d4 4s2, it is 3d5 4s1. Manganese 3d5 4s2, iron 3d6 4s2, cobalt 3d7 4s2, nickel 3d8 4s2, copper 3d10 4s1, and zinc 3d10 4s2. So this is the configuration of 3D series, L10 elements of 3D series. So here you can see there is slight change. Exceptions na ನಾವು ಜಾಸ್ತಿ ಕಾನ್ಸಂಟ್ರೇಟ್ ಮಾಡಬೇಕಾಗುತ್ತೆ because common factors na ಕೇಳೋದಕ್ಕಿಂತ exceptions ಏನಿದಾವಲ್ಲ those are being asked frequently. Chromium configuration was not expected to be so and copper configuration also was not expected to be so. Yenappa chromium configuration ನಾವು expect ಮಾಡಿದ್ದು chromium configuration we had expected it to be chromium whose atomic number is 24. The expected configuration was 3d4 4s2 ಹೌದಲ್ವಾ but it is not 3d4 4s2 it is chromium 24 it is 3d5 4s1. Now what is the reason? Now what is the reason we need to understand here? The reason is 5d orbitals alli 5 subshells ide 1 2 3 4 5. So and 4s there is one subshell. I'll take it here also to make you all understand. So 1 2 3 4 5 and 4s. So adar prakara ಮೇಲಿನ configuration expected configuration ಪ್ರಕಾರ ಏನಂತ ಬರಬೇಕದು it should come like this. Pauli's exclusion principle, filling of the pairing does not take place until it is half filled. So 6 7 I'm sorry. So it is 3d4 and 4s2. This is the configuration. Here it is 1 2 3 4 5 and then here it is 1. So if you see why the electronic configuration of chromium is this, why this is correct, why this is correct. The reason is this is attributed to the extra stability of half-filled configuration. The extra stability of half-filled 3D subshell. ನಾವು 3d5 4s1 ಮಾಡಿದಾಗ half filled 3D subshell ಏನಾಗುತ್ತೆ all the 3D subshells become half filled and half filled 3D subshells are more stable. ಯಾಕೆ they are more stable? We know the reasons also. It is one reason is it is due to symmetry and another reason is due to exchange energy. ಇದನ್ನ ನಾವು lower classes ಅಲ್ಲಿ ಕಲ್ತಿದೀವಿ 11th ಅಲ್ಲಿ. So due to these two reasons the half filled configuration and the completely filled configurations become more stable. Therefore this configuration which is to be expected is not taken, instead we take it this. Similarly with copper ಅಲ್ಲಿ configuration ಏನಾಗುತ್ತೆ 3d10 and it is 4s1. ಅಂದ್ರೆ in chromium and in copper one electron from 4s jumps into vacant or half-filled 3D subshells. So here it was expected to be like this, but here one electron from 4s jumps here and makes the configuration 3D10 4s1. Why? Extra stability. The reason is extra stability. Here it is half filled, and here in case of copper it is completely filled. Completely filled subshells athwa half filled subshells, they are more stable. The reason is due to symmetry and exchange energy. Okay. Then coming to the second transition series we call it as 4D series. 4D series. It accommodates to what? Filling of 4D subshells. 4D subshell fill agta hogutte. And here also there are 10 elements. Yavappa 10 elements. So general configuration beka, we write it as noble gas yav togotivi, we take it as krypton. Here we write 4D 1 to 10 and 5s 1 to 2. This is for 4D series. So 10 elements are there. The 10 elements are, one is, it starts from yttrium with atomic number 39 and it ends to cadmium with atomic number 48. So you need to know some of the things about 3D, 4D, 5D series. So 5D series, when we talk about 5D series, it also accommodates to what? Filling of 5D subshell. So 5D subshells fill agta hogutte. Here also there are 10 elements. Then krypton, what is the configuration? The configuration comes out to be xenon. You write noble gas score 5D 1 to 10 and 6s 1 to 2. So elements lanthanum. Please note here that it doesn't start from lanthanum. Lanthanum atomic number 57, one the element, and from hafnium atomic number 72 to mercury with atomic number 80. Illi 9 elements and this one 10 elements. You have 60 series also. There are 10 elements. Yavavappa, it starts from actinium. Atomic number 89. Actinium 1 the element too. And then from Rutherfordium, atomic number 104 to copernicium, atomic number 112. So these are about 3D series, 4D series, 5D series, and 6D series. Now, copper family elements, 3D series ali, when we talk about copper family elements. So electronic copper family elements antandre yav elements barattappa, that is first important. Copper, Ag, and Au. These are the elements which come under copper family. The copper contains completely filled 3D subshell. The common oxidation state of copper is, copper the atomic configuration, electronic configuration you nodidiri, it is 3D10 4s1. So ನಾವೇನ್ ಹೇಳಿದೀವಿ, when we are talking about the definition of D block, ಹೆಂಗ್ ಹೇಳಿದೀವಿ ನಾವು, you can see here, incompletely filled D subshell. Incompletely filled D subshell ಅಂದಿದೀವಿ. But when we see copper family elements, not only copper, ಇದು copper ಬರ್ದಿದ್ದೀನಿ, copper, silver, gold, ಯಾವುದು ಆಗಿರ್ಬೋದು, it is having completely filled D subshell. ಹಾಗಾದ್ರೆ ಅದಕ್ಕೆ ನೀವು ಹೇಗೆ D block element ಅಂತೀರಿ? So definition ಏನಂತ ಹೇಳುತ್ತೆ, incompletely filled D subshell either in their atomic state or in their most common oxidation state. Atomic state alli incompletely filled D subshell illa. It is completely filled. So let us see most common oxidation state. Most common oxidation state of copper is +2. So +2 andre 1 electron from 4s goes and 1 electron from 3D. So yenagate configuration 3D9. So it is having incompletely filled D subshell in its most common oxidation state. So this is also falling under D block elements. But when we see zinc family elements, so when we talk about zinc family elements ಅಂತಂದ್ರೆ ಯಾವ್ಯಾವಪ್ಪ, zinc ಬರುತ್ತೆ, cadmium, and then you have mercury. The configuration is 3D10 4s2. Zinc is having +1 and +2 oxidation state. Most common oxidation states yavavappa +1 and +2. So if I take +1 configuration, +1 oxidation state, the configuration comes out to be 3D10 4s1 and +2 3D10 birthday. That means electron is being removed from here. Correct? So even in their atomic state, the d orbital is completely filled. In their most common oxidation states also, d orbital is completely filled. Therefore, zinc family elements are not called as transition elements. They are d block elements, but they are not called as transition elements. Please remember this. I had told you when we were talking about family d block elements, except group 12, all the elements of D block are called transition. Why they are called transition? Why group 12 is not called transition? The reason is here. Because incompletely filled D subshell, atomic state olaganu illa, and most common oxidation states olaganu illa. Atomic state olaganu completely filled D subshell ide, and most common oxidation states olagadenu kuda completely filled D subshell irodrinda, the group 12 elements, zinc family elements, which are group 12 elements, they are not called as transition elements. Then what they are called? They are called as atypical elements. They are called as atypical elements. So with this basic introduction again of D and F block elements, let us move to the properties, physical properties of D and F block elements. Now, what are the physical properties of D and F block elements? The physical properties of D and F block elements, the first physical property is melting and boiling points. Transition elements, they have got high melting and boiling points. They are having high melting and boiling points. High melting and boiling points. It is due to strong interatomic bonding. See, they are metals. Transition elements, they are metals. So transition metals are quite hard. They are very hard. And they have, since they are hard, transition metals hard irodrinda, they are having low volatility. They are having low volatility. Correct. So since they are having low volatility, they have got very high melting and boiling points. It is due to strong interatomic bonding. So strong interatomic bonding andre enu? In transition elements, metallic bond is there. The strong metallic bond is due to involvement of unpaired electrons. It is due to involvement of unpaired electrons. So due to involvement of unpaired electrons, the metallic bonds are stronger. So in any series of transition elements, the number of unpaired electrons increases up to middle. Now we have already seen here. So in any series of transition elements, it increases up to middle. The number of elements, the number of unpaired electrons, it increases up to middle, and then it goes on decreasing. So you can see here, I can show you configuration bardaga, you can see here. So here D subshell 1 unpaired electron. Here there are 2 unpaired electrons. Here there are 3 unpaired electrons. Here there are 5 unpaired electrons. Mn is also having 5 unpaired electrons. Then 6 andaga pairing start agate. 1, 2, 3, 4, 5, 6. Then 7 andaga, I'll show you. 1, 2, 3, 4, 5, 6, 7. 8 andaga, 1, 2, 3, 4, 5, 6, 7, 8. 9, you can see here, 10 you can see here, and this is 10 again, same. So you can see here, up to middle of the series, up to D5, the number of unpaired electrons goes on increasing. So up to middle of the series, the number of unpaired electrons jasti agdang hodange, melting point also increases up to middle of the series. And then since the number of unpaired electrons goes on decreasing, here there are only 4 unpaired electrons. Here there are 3. Here there are 2. And here there are no unpaired electrons. Yes or no? So up to middle of the series, melting point goes on increasing. And then it goes on decreasing. So melting point andaga, melting point up to middle of the series. Up to middle of series, it goes on increasing and then decreases. And then it decreases. So the explanation yenappa, what is the explanation for this? More the number of unpaired electrons, stronger is the metallic bond. So more the number unpaired electrons. Stronger is metallic bond. Stronger is the metallic bond. Hence, melting point goes on increasing up to middle and then it goes on decreasing. So, but if you look at Mn, manganese and technetium, these are exceptional in their anomalous behavior. As they have anomalous values, they are having different values. So these are exceptional. When we talk about zinc, cadmium and mercury, Hg, zinc, cadmium and mercury, all the d orbitals are fully filled. Yes or no? So it is all the d orbitals are fully filled. They do not contain any unpaired electrons. They have no unpaired electrons. There are no unpaired electrons. So for covalent bonding madlike, there are no unpaired electrons, due to which the interatomic metallic bonds become weak. Since there are no unpaired electrons, the interatomic metallic bonding becomes weak. So they have low melting and boiling points. So their melting points and boiling points are low. See, atypical elements, difference in the behavior you can see. In fact, that is the reason why mercury is liquid metal. Howdenilla? Mercury is a liquid metal, is the only metal which is liquid at room temperature. Yes or no? Mercury exists as liquid metal at room temperature. Then if you see Mn, manganese, technetium and rhenium with maximum 5 unpaired electrons. They are having 5 unpaired electrons. They are having 5 unpaired electrons. So you expect what? You expect high melting and boiling points. But exceptionally, they have low melting and boiling points. Exceptionally, they have low melting and boiling points. Why? This dip in the melting point can be explained by their stable configuration. Since their configuration is stable, symmetry there, half-filled configuration is stable. Since their configuration is stable configuration irodrinda, by the virtue of which nucleus will hold the electrons tightly. So nucleus tightly electrons na hold madidike, there is less delocalization of electrons and metallic bond is much weaker. So here again you have tungsten. If you look at tungsten, symbol is W. This, why I said tungsten? Because this is the metal with highest melting point. Highest melting point. Out of all metals, tungsten is having highest melting point. Yes, 3380 degrees Celsius. And mercury, as we said, it is a liquid metal. It is having lowest melting point. So what is the melting point? Do you all know what is the melting point? It is minus 39 degrees Celsius. It is minus 39 degrees Celsius. So this is all about the melting and boiling points. Next concept, what I'm going to talk about is occurrence and abundance. So occurrence, you might be knowing about occurrence of these elements, transition elements. 3 of the transition metals, they are very abundant in the Earth's crust. 3 of the transition elements are very abundant in the Earth's crust. Iron is 4th abundant element. Then titanium is 9th abundant element. Then Mn is 12th abundant element. See, these 3, they are most abundant elements found in the Earth's crust by weight. Iron is 4th, titanium is 9th, Mn, manganese is 12th. Second and third transition series. When we talk about second and third, andre 4D and 5D series ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ, they are much less abundant compared to 3D. They are less abundant compared to 3D elements. Okay. Technetium does not occur in nature. It is the first man-made element. Technetium doesn't occur in nature. It is first man-made element. Sorry, it is the first man-made element. So transition metals, how they occur in the Earth's crust? They occur in the combined states. They are not found in the free states. Like for example, exception gold, silver is found in free state. But transition elements, group 3 to group 11 elements in transition antivala, they are found in a combined state. They are found as oxides. They are found as sulfides. They are found as carbonates. Okay, so they are found in combined states. Example, ನಿಮಗೆ ಗೊತ್ತಿದೆ, you already know iron, hematite ore of iron, Fe2O3, hematite ore. Then CuFeS2, copper pyrites antivi, chalcopyrites. Then silver Ag2S, silver glance antivi. Then you have BiAu2. This is bismuth orite, gold. Then mercury cinnabar, HGS. Then zinc ZnO oxide. Then Mn, it is MnO2, pyrolusite. These are all the ores of different transition elements. You can see they are either found in oxides or sulfides, and some are in carbonate form also. What are the uses of these? Let me recapitulate some of the uses also. These are mostly used to make alloys. So you can see titanium metal and its alloy. So here titanium and its alloy with alloying with aluminium. When you take titanium alloy with aluminium, aircraft industrially for a jet manufacturing and gas turbine engines, this is being used. So this is the first application. Then niobium alloyed with zirconium. I'm sorry, zirconium, Zr. It is a superconductor at low temperature. Then tantalum, tantalum. These are all elements of D block elements, what I'm talking about. Tantalum is used for making metal plates and screws and wires. For fractured bones use all the screws haktare, nut bolt haktare anta kelidiralla, rod kundrisidru. All those screws and all are to fractured bones. What are being used? They are made up of tantalum metal, which is also a D block element. Chromium is used in chrome plating. Zinc also is used in electroplating to prevent rusting of iron, which is being used. Zinc is used for galvanization of iron. Rust agaldage nodkolike. Yes. Then molybdenum and tungsten, they are used alloyed with steel. Molybdenum and tungsten alloyed with the steel, they give very hard alloy and is used for cutting steels, again for cutting different steels. Tungsten carbide, WC, it is used extremely hard. It is used for drilling instruments. Then most of the elements, most of the transition metals and their compounds are used as catalysts. They are used as catalyst. Like for example, manganese dioxide, MnO2, it is used as catalyst. Rhenium, it is used. All platinum metals, all transition metals they have catalytic property. We'll discuss this in detail also. Now, mundin synopsis we'll talk about it. Iron is used in steel making. It is important in plants, important element in plants and animals also. Hemoglobin, it is made up of iron only, yes or no? Heme stands for iron, globin stands for protein. So heme, iron iddalli hemoglobin secretion jasti irate. Otherwise you will see a person suffering from anemia, low hemoglobin, because of less secretion of iron, less deficiency of iron, you can say. Then cobalt, it is used for making magnetic alloys. Cobalt, it is used for making magnetic alloys. Cancerous tumors in hogladsike, what we use is, we use cobalt there also. Then, so these are all the applications. We'll discuss why this cobalt is not just used like that only. Then the catalytic properties of why MnO2 is being used. What is the reason that all the transition elements are having so much high catalytic property? That all will be discussing one by one. So first general characteristics is atomic radii, atomic or ionic radii. All these general characteristics are based upon the electronic configuration of the elements, transition elements. So along the transition series, the atomic radii first decreases. When you move along the transition series, atomic radius first decreases, remains constant almost up to end, remains constant up to end, and then it increases slightly. If you want to look at the atomic radii, I can tell you the atomic radius scan. How do you remember? Sk, T, V, Kr, Man, Fe, Ko, Ni, Ku, Zen. So these 10 elements, if you see, the atomic radii is measured in picometers. 10 raised to minus 12 meters is 1 picometer. So here scandium, it is 144 picometer, titanium 132, vanadium 122, chromium 117, manganese 117, iron 117, cobalt, it is 116 if I'm not wrong, nickel 115, then copper 117, zinc 125. So you can see here atomic radii atomic radii, it is going on decreasing up to middle. So it is remaining constant here. It is remaining almost constant, and slowly again it is increasing here. Why it is happening? So what is the reason for this? The reason is very depending on electronic configuration. The newly added electron enters into inner 3D subshell, correct? Inner 3D subshell alli electron enter agate. So inner 3D subshell andre yavdu n-1th shell, D subshell. The electron is entering here, correct? So thus it will screen the outer 4s electron. So outer 4s electrons na 4s2 electrons idavala. So it will screen the inner 3D electrons. It will screening effect kaltidiri. It will screen the outer 4s electrons. With increase in atomic number, ಹೇಗೆ ನಾವು ಲೆಫ್ಟ್ ಟು ರೈಟ್ ಹೋಗ್ತೀವಿ, there is increase in the atomic number. Z is increasing continuously by one value, 21, 22, 23 ಅಲ್ಲ, it is going on increasing, yes or no? So with the increase in atomic number, nuclear charge is also increasing by one number. ಪ್ರತಿಯೊಂದಕ್ಕೂ ನ್ಯೂಕ್ಲಿಯರ್ ಚಾರ್ಜ್ ಒನ್ ನಂಬರ್ ಲಿಂದ ಹೆಚ್ಚಿಗೆ ಆಗ್ತಾ ಇದೆ. 21 ಇಂದ 22 ಪ್ಲಸ್ 1, 22 ಲಿಂದ 23 ಪ್ಲಸ್ 1. ಸೊ ಇಟ್ ಇಸ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಬೈ 1. ದಟ್ ಮೀನ್ಸ್ here the nuclear charge is increasing. The screening effect caused by 3D electrons, the screening effect caused by 3D electrons in the beginning is less significant. Up to chromium it is less significant. ಯಾಕಂದ್ರೆ electrons ಕಡಿಮೆ ಇದಾವೆ. 3D1, 3D2, 3D3, 3D5. So up to chromium electrons ಕಡಿಮೆ ಇರೋದ್ರಿಂದ electron repulsion is less. Electron repulsion is less. It is not significant as there is no pairing. But from manganese, if you see, from manganese also it is 3D5. From iron, if you see, pairing occurs. So pairing adaga effective. So here effective up to chromium effective nuclear charge. Hege denote ಮಾಡ್ತೀವಿ? Up to chromium effective nuclear charge increases. So effective nuclear charge ಜಾಸ್ತಿ ಆದಂಗೆ ಏನಾಗುತ್ತೆ, effective nuclear charge increase ಆದಂಗೆ size goes on decreasing because it will pull the electron much strongly. So it will pull the electron much strongly. Effective nuclear charge ಜಾಸ್ತಿ ಇದ್ದಾಗ so the electrons are being pulled much strongly, therefore size goes on decreasing, and you can see here decrease in size. But from manganese onwards, pairing of the electrons takes place. Electron repulsion ಜಾಸ್ತಿ ಆಗುತ್ತೆ. So increase in size, so decrease in size. The decrease in size due to increase in charge is counteracted. It is counteracted. It is dominated by increase in size due to increase in screening effect. I hope you might be knowing the symbol for screening effect, right? Screening effect symbol enu hige bariತೀವಿ ನಾವು. Screening effect and also electron repulsion. So in the beginning, ಯಾವುದು dominant ಇದೆ? The dominant factor ಯಾವುದು? In the beginning of the series, dominant factor is effective nuclear charge. So effective nuclear charge ಜಾಸ್ತಿ ಆದಂಗೆ size ಕಮ್ಮಿ ಆಗುತ್ತೆ. But since electrons ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ from manganese onwards, and there is pairing of the electrons also, so increase in size due to increase in the screening effect and also because of electron repulsion. So this is the trend of atomic radii in the 3D series. In the 3D series. So atomic radii remains almost constant from chromium up to copper. At the end, that is copper, all the electrons get paired and electron repulsion will be maximum. Here, the electron repulsion yenagate, it will be maximum. Electron repulsion will be maximum. Therefore, to overcome this electron repulsion, the electron cloud slightly expands. The electron cloud slightly expands. So expand admele yenagate size, the atomic size slightly increases, and you can see that increase in the atomic size here. Copper atomic size is 117 and zinc atomic size is 125. Down the group, when you talk about down the group, 4 series baruttala, 3D series, 4D series, 5D series and 6D series. Down the group, atomic size generally increases. That is basic thing. Yeah, okay? Because when you move down the group, the electron enters into the new shell. The electron, nodi, 3D series. Then you have 4D, 4th subshell, size jasti. 5D series, 5th subshell, size slightly jasti agate. So across the period, explanation is here. Down the group, the atomic radii Down the group, atomic radii goes on increasing. It goes on increasing. But when we talk about 4D and 5D series, elements almost have same atomic size. That we'll discuss again in detail now, because that is due to lanthanide contraction antivo. It is due to lanthanide contraction. Lanthanide contraction again, when we talk about F block elements, we'll be discussing there. Fine. Coming to the next property, that is ionization enthalpy. ಅಥವಾ ನೀವು ಅದಕ್ಕೆ ionization energy ಅನ್ಬೋದು. Ionization energy of all transition metals are higher. They are higher than S block. Yes, we know it. Quite obvious, ಹೌದಲ್ವಾ? Because across the period, atomic size ಕಡಿಮೆ ಆಗ್ತಾ ಹೋದಂಗೆ ionization energy, that is the energy required. Ionization energy ಅಂದ್ರೆ ಏನು? First, energy required to remove the last electron, differentiating electron ನ ತೆಗಿಲಿಕ್ಕೆ what energy you put, that is called ionization energy, ಹೌದಲ್ವಾ? So here, ionization energy of the transition metals are higher than those of S and P block elements. As S block elements, these S block elements na nodidaga, S block elements, they are highly electropositive. But D block elements, they are less electropositive than S block elements because across the periods, across the series. Now, when you talk about along 3D series, D block alline matartirbekadre, along 3D series, transition elements, ionization energy of the transition elements, it increases. Ionization energy goes on increasing. Why it increases? It is due to increase in nuclear charge experienced by the outer 4s electrons. So screening effect caused by filling of inner d orbitals partially decreases the effective nuclear charge. So effective nuclear charge ಹೆಚ್ಚಿಗೆ ಆದಂಗೆ, but not to an extent. It will increase, but it will not it will not increase to an extent noticed in 2 and 3 group elements, 3 period elements. Therefore, we say ionization energy increases gradually with increase in atomic number. Means relative difference between the successive elements, it is very less. It is very less. So ionization energy ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ S and P block elements ionization energy ಹೇಗೆ ನಾವು exactly ಹೀಗೆ ವೇರಿ ಆಗುತ್ತೆ ಅಂತ ಹೇಳ್ತೀವಲ್ಲ, ಹಾಗೆ ಹೇಳಕ್ ಬರಲ್ಲ ಇಲ್ಲಿ. It is because of the size, atomic size. Compared to S block elements, the ionization energy is higher. It is higher. Yake? Because size is less compared to S block elements. Okay. Then coming to the next property, that is very important, oxidation state. This is very important property, oxidation states. Okay. So oxidation state anta andre enu? See, it is the hypothetical charge which is possessed by an atom. Charge possessed by an atom, which tells you the number of atoms it is going to bond with. Okay. So when we talk about the oxidation states of transition elements, transition metals exhibit variable oxidation states. Either point, this is very important. All the transition elements exhibit variable oxidation states. Because of this one reason, because of this one reason, there are various properties shown by transition elements. So why transition elements show variable oxidation states? Transition elements, yaake variable oxidation states torsate? Let me take an example. You take example of manganese, Mn. There are many compounds of manganese, like MnO is there. You have MnO2, Mn2O3. Let me make it much specific. So you have Mn2O3, you have Mn O2, you have Mn2O7. So these are different compounds of manganese. So if you see here, the Mn, manganese in MnO, it is having +2 oxidation state. Mn2O3 is +3, Mn O2 is +4, Mn2O7 is +7. So you can see variable oxidation states. This is not the case in S and P block elements. Howdalva? S block elements alli yenagatte? S block lithium, it is +1 only. Always in yaude compound of lithium togolli, lithium chloride togolri, lithium bromide togolri, lithium oxide togolri. Any compound of lithium is having +1 oxidation state. Any compound of magnesium you take, it is +2. It is fixed. Any compound of aluminum you take, it is +3. So oxidation states fixed idave for S and P block. But if you talk about D block elements are having variable oxidation states. They exhibit different oxidation states in different compounds. Why they exhibit different oxidation states? Oxidation states ಹೇಗೆ ತೋರ್ಸಪ್ಪ? Lithium is showing +2 oxidation state because its configuration is 1s2, 2s1. By losing one electron, it is having one unpaired electron. By losing this one electron, it will have stable configuration ಅಂತ ಅಂತೀವಿ. And apart from that, if you see, the energy difference between 1s and 2s is very large. ಬಹಳ ಜಾಸ್ತಿ ಎನರ್ಜಿ ಡಿಫರೆನ್ಸ್ ಇರೋದ್ರಿಂದ between 1s and 2s orbital, only this electrons can be lost. ಜಾಸ್ತಿ ಎನರ್ಜಿ ಇರೋ electron ನ ತೆಗಿಬಹುದು. If you want to remove this electron, you need very high amount of energy, which you call it as ionization energy. So first ionization energy, electron can be lost very easily. The second ionization energy is very high. So that becomes difficult here. Same with the case of magnesium. Magnesium valaga nodidre ನೀವು, it is 1s2, 2s2. You can remove first electron by using first ionization energy. It becomes Mg plus. But Mg plus is highly unstable because it is having 2s1. So you can remove this one electron also using the second ionization energy and form Mg plus 2. So when you remove two electrons, it is 1s2. This becomes stable configuration. This is one reason. And the energy difference between first shell and second shell is very high. That is, energy difference between n minus 1th shell and nth shell is very high. So this electron cannot be removed that easily. Very high amount of energy is required. But this is not the case in D block elements. When we are talking about D block elements, let us try to explain why D block elements show variable oxidation states. When we are talking about D block elements, the energy difference between n minus 1d and ns subshell is very small. So energy difference ಬಹಳ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ, in addition to ns electrons, n minus 1d electrons are also lost. N minus 1d electrons are also lost. They also participate in bonding. So when two ns electrons are lost, the transition state is +2. When two ns electrons, yes, I hope this point is getting clear for you. When two ns electrons and one 3d electron is lost, the configuration becomes +3. When two ns electrons and two 3d electrons are lost, the configuration becomes +4. Getting? Therefore, since very important, what is the reason? The reason is the energy difference between n minus 1d and ns subshell is very small. Since the energy difference is very small, along with the ns electrons, n minus 1d electrons also participate in bonding. Therefore, the variable oxidation states are being seen. Oxidation states are seen. So elements at the beginning of the and at the end of the transition metals, if you see, they have got few number of electrons to lose or to share. Thus they exhibit lower oxidation, less number of oxidation states. Now elements in a node 3D series alli, they are having less number of electrons to be lost at the beginning and at the end. At the beginning agirbodu, at the end agirbodu, they are having less number of electrons to be lost. Therefore, they will exhibit less oxidation states. Scandium, if you see, let us make it very clear. Okay. Scandium, let me take example. Scandium, Ar18, 3d1, 4s2, 4s2. So here, these three electrons can be lost. Therefore, scandium can show the all the three electrons can be lost. So it can exhibit the oxidation state of +3. Similarly, titanium, if you take, it is 3d2, 4s2. It can lose 2 electrons and form +2 oxidation state. It can lose 2 electrons from 4s and 1 from 3d and form +3 oxidation state. It can lose 2 electrons from 4s and 2 from 3d and form +4 oxidation state also. Are you getting this? Therefore, titanium is showing variable oxidation state. Then cobalt, nickel, copper. Cobalt, nickel, copper, if you see, they can exhibit mainly +2 and +3 oxidation states only. They can exhibit +2 or +3. Copper exists in +1 and +2. Copper. Then iron, if you see, it exists in +2 and +3 oxidation state. Zinc is the atypical element. It is having only +2. See again, difference in the behavior. Transition elements annala, we call it as a atypical element because it is having only one oxidation state, whereas all the other elements, scandium also, it can show +2 and +3. So it can show only +2 oxidation state, whereas the rest of the D block elements, they can exhibit more number of oxidation states. But in the beginning of each series, then less number of oxidation states are shown because less number of unpaired electrons in 3D. And at the end also, less number of oxidation states because less number of unpaired electrons. But in the middle of the series, like for example, in the previous slide you have seen, Mn +2, +3, +4, +7. So many oxidation states can be shown. So in each series, maximum common oxidation, so the common oxidation state shown by any transition element is +2. Excuse me. The tendency to exhibit highest oxidation state increases up to middle, reaches maximum and then decreases. Maximum oxidation state eshtiruttappa? It is the sum of n-1d electrons and ns electrons of the subshell. ns subshell olagirtakanta sum n-1d ಮತ್ತು ns subshell olagirtakanta electrons ನ total ಮಾಡಿದಾಗ you will get what you will get? Maximum oxidation state shown by the elements. Now, which is the highest oxidation state shown by 3D series? Highest oxidation state shown by 3D series is Mn. Mn shows the highest oxidation state of +7. In certain compounds, transition metals exhibit zero oxidation state, but overall transition metals nodidaga highest oxidation state is shown by it is +8. Yav elements torsutappa? It is ruthenium and osmium. It is ruthenium and osmium. They show oxidation state of +8. But when we talk about 3D series, highest is shown by Mn, that is +7. In certain compounds, transition metals also exhibit zero oxidation state. And this we will be discussing in the coming chapter, that is coordination compounds. Coordination compounds. That is the reason why they form coordination compounds, zero oxidation state. So, transition elements in their lower oxidation states. Lower, yaudadru transition element with oxidation state kadme ide, it is that compound is ionic in nature. Higher oxidation state ittappa antandre, it will be covalent. Please do remember. Andre, Mn +2 +3 is ionic. Mn +7, it is covalent. Okay. All the transition metals, they exhibit highest oxidation states with the compounds of fluorine and oxygen. You know why? Because these are highly electronegative. That is the reason why they exhibit highest oxidation states here. So this is about some of the properties of transition elements, some of the properties. So here the transition elements have high melting and boiling points due to strong interatomic bonding. We have discussed atomic and ionic radii of transition elements are smaller than those of S block, but larger than P block. And even in transition elements, there is variation. Up to middle of the series, it goes on decreasing. It remains constant, and at the end, it goes on increasing. And we have also seen the properties also. Ionization enthalpies are very high, again due to strong interatomic bonding. Among elements of first transition series, zinc has the least enthalpy of atomization. Atomization, it is related with the electrode potentials. Those we will be taking up in the next class. We will be discussing the remaining properties of the synopsis, the remaining properties of D and F block. The synopsis will be taken in the next class. For now, I hope some of the points which we have discussed, they are clear. Thank you. In the next class, we'll meet up with the next properties of D and F block elements. Thank you once again.